Hi, I'm Sam Moyer and I'm going to be discussing the Flyby Anomaly. The Flyby Anomaly is the unexpected change in velocity before and after the perigee of the orbit. The perigee of the orbit is the closest point a satellite is with respect to the Earth. Flyby Anomaly uses the perigee of the orbit to discuss the unexpected change in velocities, as that is the greatest unexpected change in velocity of the orbit. Anderson formula is the most well-known formula of the flyby anomaly, and this is his formula for the anomalous velocity variation, with v sub infinity being the velocity at the perigee, and with these being the declination of the incoming and outgoing velocities, and k being a constant, which is equal to 3.099 times 10 to the 6 per second. On the 9 flyby missions recorded, the formula produced an error of 1.67%. This 1.6% was relating the observed delta V to the expected delta V. According to Aikido, the velocity of a spacecraft orbiting around the perigee is dv over dt equal to mu e of the Earth over all ball over all cubed plus the acceleration from the tidal forces plus the acceleration from the geopotential forces, with the force term being the acceleration from the force of gravity. The force of gravity is equal to the gravitational constant times the mass of the Earth times the mass of the object orbiting the Earth, in this case the satellite. The differential force, or known as the tidal force, is the derivative of the force of gravity with respect to all, which is equal to two times the gravitational constant times the mass of the Earth times mass of the object over all cubed dr. According to Aikido, a more precise measurement for the tidal acceleration is this equation right here, with mu being the mass constant of the sun and moon, and capital R being the radius of the Earth, little r being the position from the Earth to the satellite. Capital R bar is the radius of the celestial body, so in this case the moon or the sun, and little r bar is the positioning from the celestial body to the satellite, so the distance from the sun's surface to the satellite. Another effect that has to be taken in is the geopotential. Geopotential has to be taken in effect because the Earth is inhomogeneous distribution of mass, meaning that the Earth doesn't have a constant gravity over the whole surface. Due to the homogeneous nature of the Earth, this causes the gravitational force to be different at different parts of the Earth due to the densities of material underneath the surface. The publication from the NASA, GSFC, and NIMA joint geopotential model in 1996 produced a geopotential of this equation. The equation that was used was based off of gravitational potential, which is the mass constant of the Earth over radius r above the Earth to the satellite. If you take the gradient of the potential, it produces the perturbing forces in each direction. So the force of the geopotential is in the r direction, theta hat direction, and lambda hat direction. In this case, Akita uses the facing westwards on the Earth to be positive lambda. So since we're in spherical coordinates, we have to take the spherical gradient. So in the r direction, it's thus the negative derivative with respect to. It's the negative partial derivative with respect to r of the gravitational potential, which produces this equation. And then you have the force of theta, which is the negative 1 over r of the partial derivative of the potential with respect to theta. And then you have the force in the lambda direction, which is negative 1 over r sine of theta with the partial derivative of the potential with respect to lambda. Using this equation, we can find the acceleration off the geopotential of the Earth. And another effect that can have an effect on the satellites is the atmospheric friction, which can be represented by the equation for drag, which is the negative 1/2 atmospheric density times velocity squared times the cross-section area of the satellite times the coefficient of drag, which in this case is roughly around 2 for almost all satellites. On the NEO spacecraft, we can plug in the constants to produce a acceleration of 1.02 times 10 to the negative 10 kilometers per second squared. Due to the small impact from the atmospheric friction of the NEO spacecraft, since it was above 500 kilometers, we can neglect the effect from atmospheric friction for most spacecraft as they orbit around the Earth at a higher altitude than 500 kilometers. Other effects that could have a small impact on the Flyby Anomaly are the tidal forces from other planets. In this case, Jupiter, which produces a tidal force of 1.63 times 10 to the negative 10 kilometers per second squared, which is again a small number, so that can be negotiable. That can be neglected. Other forces that can be neglected are ocean tides and thermal radiation. The effects of these are even smaller than the tidal forces from other planets like Jupiter. Possible sources of the anomaly is the fifth force that Akita theorizes that we cannot measure yet and is impacting the Flyby Anomaly. And the second one is extensions of general relativity. As we understand general relativity more, this can help us understand what is causing the Flyby Anomaly in the future.